introduction. So my name is Hanrui. So my office is just in the 38th building. So I know probably less than on quantum than your guys. So I just trying to do some quantum architecture research, like you guys are doing the device, and also some of others doing the algorithm side. So we try to do some compilations in the middle. So for example, the qubit mapping and also instruction scheduling and design ONSAT for the variational quantum circuits, and also like the pulse generation, optimal control. So those are the new area. So I think in the recent several years of architecture community, they try to extend the people doing the quantum system research. So I'm the one of the member of that. And also my advisor is Professor Song Han, who is also joining the MIT Center for Quantum Engineering. So I will be like join all the journal clubs and also the group meetings later. So okay. Today I'm going to first introduce a recent work of us, which is QuantumNAS, noise-aware search for robust quantum circuits. And also we have a library based on PyTorch, so to do the fast simulation of the quantum circuits on GPUs and also get the gradients of the parameters in the circuits. Okay, so let's get started. So in terms of the background, so as we know, we're in the NISQ era, so we have noisy qubits and also a limited number of qubits. So in order to achieve, so in terms of the error rate, I'm sure you know all of this, but just to spend 1 minute to reiterate it. So the gate error rate is around 10 to the power of -2 to -3. Those are the IBM machines. I'm sure you guys can do better than that. And also limited number of qubits, which is from tens to hundreds. For the current machines, many of the algorithms we're trying to do to demonstrate quantum advantage of variational quantum circuits or parameterized quantum circuits. So that contains the fixed gates and also parameterized gates. So those parameterized quantum circuits are commonly used in hybrid classical and quantum algorithms, such as the variational quantum gate solver for quantum chemistry and also quantum neural nets for machine learning, QAOA for optimization problems. So we find that the challenge of the PQC is still two parts. One part is the large noise of the system. So here we show an example using the quantum neural nets to do the classification of the handwriting digits, which is a very old class like task in the machine learning community. So we try to do the classification of the handwriting digits from 0 to 4, 0 to 3. And then we can see that the x-axis is the number of parameters in the circuits, and the y-axis is the accuracy of the classification. So in the green curve on the top of that, we see that the noise-free simulation of the circuits, when we increase number of parameters, the learning capacity increases. So we can see higher accuracy. But on the real machine, which is a superconducting IBM Yorktown machine with 5 qubits, we can see the accuracy actually goes up first and then degrades to a pretty low level, which is barely the random guess, 25%. Yeah.
So what are the parameters here?
The parameters are the rotation phases.
Okay.
Right. So we use the rotation.
The number, you have a bunch of different gates that you apply.
Yes.
So I could also read it as number of gates.
Yeah, that's proportional to the number of gates. Right. Yeah.
And how many qubits?
The 4 qubits. Yeah. Cool. So we can see that there is a large gap between the noise-free simulation and also the measurement on the real machine. So we try to design a circuit with a good trade-off, because we know that when we increase the number of gates, the learning capacity of the circuit is larger, but that also introduces more gate error. So we try to find a sweet spot which can balance the noise and also the learning capacity. So that is not very easy, because we know the large design space of the parameterized quantum circuits. We have different types of gates, all different ways, all different types of gates, from U3 gates to NOT gate, CZ gates. And also we can have different number of gates in the circuits. For example, if we just use 8 gates, or we use 16 gates, or we just concatenate the same blocks for many times, so we can have many different number of gates in the parameterized quantum circuits. And also the positions of the gates is also tunable. Say we can, even we have the same number of gates and also the same type of gates, we can put them to the different locations. So that will also like cover different space of the Hamiltonian space. So our idea is that how can we do the search of the best quantum circuits in the existence of the noise? So for example, we can, how can we design the ansatz to make sure the ansatz can run best on the target machine? So one naive way is to just, you can random search or random pick many of the candidates, and then you do the training of the parameters of the phases of the rotation gates, and then you test, you see the final performance on the real machine, and then you pick the best one. But what is the problem with that? We have to train many of the candidates, right? For one candidate, we need to do the training. Another one, we also do the training again. So in that case, we have to spend a very large amount of time to do the training in order to do the search. So our motivation is how to make this whole process more efficient and faster. So so that is the goal of the QuantumNAS, which is automatically and also efficiently do the search. And our search goal is noise robust quantum circuits ansatz for the different kinds of variational quantum algorithms. So the first part, automatically and efficiently, is achieved by one circuit, which is called SuperCircuit, and it can provide parameters to many of the candidates. So the idea is that say we already have a design space, and then many of the candidates in the design space, they actually share some of the structure, share some of the gates. So our idea is how to train those parameters for once, and then for each candidate we can just inherit the parameters from the SuperCircuit, and then we can test the performance on the real machine. So in that case, we just train for once, and then train the parameters for once, and then use that to evaluate for many times. So that is more efficient than train many times, evaluate many times. So for the noise robust part, we can involve the noise feedback in the search loop, so that when we do the search, we just evaluate that on the real machine, and then see which one performs the best on the real machine, and then we use that. And the second is co-search of the circuit architecture or the circuit ansatz with the qubit mapping. So qubit mapping is the mapping between the logical qubits to the physical ones. So we do a co-search of the ansatz with the qubit mapping to further enlarge the design space and try to find the most noise robust one. Okay, so there are 4 steps in the QuantumNAS. The first step is to construct the SuperCircuit, which we just mentioned, and do the training. The second step is to, after we have the SuperCircuit, we want to do the search, right? We want to search for the most noise robust one. So we have we use a evolutionary search engine to do the co-search of SubCircuit ansatz and the qubit mapping. And the third step is just to train the search the SubCircuit from scratch, so that we can get the final performance and then see what is the accuracy or the expected value on the real machine. And the final step is to do some quantum pruning. So the final step is actually orthogonal to the previous 3. So the quantum gate pruning is just can be applied to any of the variational circuits. So, but here we also propose here to do some fine-grained like pruning or the changing of the architecture ansatz. Okay, so the first step is the SuperCircuit and SuperCircuit construction and training. So firstly, as a predefined space, we have to have a like design space. So which means we need to constrain from the arbitrary large space to just several size of the gates. For example, we need to predefine what kinds of gates we want to use. Not any of the gates, but just specify that to a limited number of gates we can use. But that still construct a pretty large space. Here we have an example for the U3 and CU3 gates. So for example, in the this is the simplest one. We can have say 4 U3 gates in the first layer, and then 4 CO3 gates in the second layer. And then we can use any of the subset of the gates. Say we can just use, say the gates 2, 3, 5, 6, 8, and 8, or the gates 1, 5, 6, 7, 8. So we know that the performance of those different gates will be pretty different. So, but they all kinds of can inherit the weights from the SuperCircuit. So in that case, we just need to train the parameters for once, and then when we have a new candidate in the design space, we just inherit the parameters to the SuperCircuit, and then we evaluate the performance on the real machine. Okay, so as we introduced before, the motivation for SuperCircuit is to enable the efficient search of the architecture candidates without training each of them. So, and then the SuperCircuit inherits parameters, and then there is a hypothesis here. With the inherited parameters, we need to make sure that the performance of the SuperCircuit with inherited parameters is somehow order preserving to the final performance if we train them from scratch. In that case, we use the inherited parameters, and then we find the best one, and we assume that one is also the best one if we train all of them from scratch. So we will show an empirical result of that. Actually, this hypothesis is the foundation of this method, which means we don't need to train all of the parameters. We just train to some level, and then those are order preserving, so we can already use them to find the good one. Okay, so during the SuperCircuit training, we actually have two steps. The first one is to sample a gate subset of the SuperCircuit, which is the SubCircuit. So we do the sample of the SuperCircuit, and then we train that for one step. Right? So we only use the subset to perform the task, and then to update the parameters in the subset. So that is just for one step. And next step, we will sample a new set of gates, and then we just use that set of gates to do one forward pass, and then do one update step of the parameters. So we have an animation later. So before that, I'm just going to introduce two small techniques to stabilize the training process. The first one is called front sampling. The front sampling is that during the training process, we need to sample SuperCircuit. But for example, if we decide to sample 6 blocks, and then the whole design space contains, say, 100 blocks, and then we will just use the first 6 blocks to do the training step. So that is the front blocks. And also inside each layer, if we decide to use, say, 2 gates in the first layer, we also just use the front gates, like gate 1, gate 2. And for the second layer here, if we decide to use, say, 3 gates, we use the gate 1, gate 2, and gate 3. So that is the front sampling. The intuition is to make sure the overlap between the SuperCircuit can be somehow increased, so that the training process can be stabilized. And also another idea is restricted sampling. So because we need to sample one SuperCircuit at each time step, so if the 2 consecutive sampled SuperCircuit are drastically different, and we know that the training process will be also very unstable. So we want to restrict what is the maximum number of different layers between 2 steps. So say here, if we restrict to 4 different layers, so here the circuit here is 3 gates here, 2 gates here, 4 and 3. And next step, we sample a new circuit with this new ansatz with this structure. And then we know that there are 5 different layers. So we will not use this because they are too different, and we cannot train that stably. So we will just discard that, and then do a sample again to the bottom one, and then do one step of the parameter update. And then next step, if we sample a new circuit with just 2 different layers, that is okay. So we just update parameters with the new circuit. Okay, so here is the animation for the training and the sampling and training step. So for example, we have like each step, we just sample the gates, like the solid gates, and then we update parameters, and then we go to the next step, and then we do the sample again, and then update parameters. So this whole process is trying to obtain a set of parameters in the SuperCircuit so that we can use that later to search for the best one. So in order to further elaborate this, we also have a small example. We just show the parameters in the first layer. So the parameters are actually updated accumulatively. So which means after the first step, if some of the gates are not used, they will just keep the same parameter of the previous step. So say in the first row here, we have the 2 gates sampled, and then we use red color to indicate that the parameters is updated. So we update 2 gates, and then we update the 3 ground gates, and then we update the first sample gates. But for those parameters, so for those 3 steps, we don't have a chance to sample the last gate. We just keep the parameter the same. And in the next step, if we have the chance to sample 4 gates in the first layer, we will use all those four gates to do the task, and then update all the 4 parameters.
Next question.
Yeah.
So what is determining whether the parameters are updated? Because like from the diagrams, it seems like.
That's just random sampling actually. So so this is one SuperCircuit on-site, right? This is another SuperCircuit. So during the sampling, we do the random sampling with some constraints, like the restricted layer constraint. So we just randomly select that next one, and then if the next one is justly different, and then we discard it, and then randomly select another one. So that process is random. Yeah. Cool. Any other questions? Okay, so as we mentioned before, we have a very important hypothesis, which is that the performance with the inherited weights or the inherited parameters is order preserving to the final performance. So here we show some empirical result. So the x-axis here is the SuperCircuit performance with inherited parameters from the SuperCircuit, we just trained, right? And the y-axis is the SuperCircuit performance trained from scratch, which means we just take that SuperCircuit on-site, and then we do all the training of all the parameters inside that on-site. And then we, for each of the point here, we show the performance of one SuperCircuit we sample from the space. So we can see that we compute the Spearman correlation coefficient between those 2 performance. And we can see the coefficient is typically larger than 0.7. Some of them is 0.9. So we can see a pretty positive correlation between the 2 performance. So in that case, we can use the partially trained. Yeah, question?
I was wondering if you, so if you do this SuperCircuit training and then you just take a SuperCircuit with
right.
the same parameters, could you then like do some small amount of additional training based on that SuperCircuit, kind of like in transfer learning? Right?
Oh yeah, that's a great question. So yeah, actually that's true. So the whole the whole process is trying to find the on-site, right? So after we find the best on-site, we can just inherit the parameters from SuperCircuit and then do some steps of fine-tuning. So that is very practical to reduce the overall cost. Yeah. But in our case, in order to make sure the fair comparison to other baselines, we just make sure the benefits comes purely from the on-site difference. So we also do the train from scratch. But in practical, we can do that, train just inherit ways and then fine-tuning with less number of steps. Cool. Okay, so so we know that the order preserving property of the SuperCircuit weights is roughly good, and then we can use that to search for some good SuperCircuit. So for example, in this case, or that case, we find one with the best one, which is that one, and then we train the circuits to the end, and then we can see the performance is also the best one. So we hope that's the case for all the other tasks and also all the other variational quantum algorithms. So we have some evaluations later. Okay, so that's a part of the SuperCircuit training, and then after that, the next step is to do some search. So this is the topology of the quantum IBM Yorktown machine, which contains 5 qubits. So the search space contains both the qubit mapping, which I show there with different colors of the circles, like the lines are the logical qubits, and then we can map to different physical qubits. And also we can also search for different SuperCircuit ansatz. So we use a traditional, like widely used evolutionary search engine, so which can propose the architecture of the SuperCircuit and also the qubit mapping pairs. So that will be, the information will be embedded in the vector, which is called gene. And then we can send the SuperCircuit and also qubit mapping to the evaluator. So the evaluator will get parameters from the SuperCircuit we just trained. And then we can evaluate the SuperCircuit with the qubit mapping on the real quantum machine, or we can use the noise simulator with noise model. So in that case, we involve the noise information of the target machine to the search loop. So after the evaluation, we can feedback the performance of the SuperCircuit and also qubit mapping pair to the evolutionary search engine. And then we can do some standard mutation and crossover, which are shown here. The mutation is just to do some arbitrary or random change mutate of the circuit ansatz of each layer. So, and then the crossover, we take 2 parents from the parent population and then generate a new data point from those 2 parents. Yeah.
When you do this qubit mapping, do you consider the connectivity of your device as like a constraint, or would that become into the optimization?
Right. So the qubit mapping here is the initial mapping for the circuit. So we just specify the initial mapping to the Qiskit transpiler, and then we use the transpiler to do the underlying, like the insert swaps or other compilation process.
Yeah, so how fast is this chain? Because those evolutionary searches are very slow and costly.
Right. Yeah, so for our case, we have a timetable later, but so this process is done on GPU, so we can do the batch processing. So that's pretty fast, but I would say that's a very good question, very good point, because if we want to scale up to large circuit, we need to do all the process on real machine. So we can do the SuperCircuit training with, say, parameter shift on real machine and all the steps on real machine. So the evolutionary search may be the bottleneck, but that part, like evolution engine part, will still on the classical side to generate the ansatz. So the evaluation part may be slower because we need to run that on real machine. Yeah. Mm-hmm. Right. Actually, I want to add one point here. So the search algorithm is also like orthogonal. Like evolution is orthogonal to this search method. We can use others like the Bayesian optimization or reinforced learning. So any optimization here can leverage the SuperCircuit. Yeah. Okay. So after we do many iterations of the search process, we can obtain the one searched SuperCircuit, which is our final, like best, hopefully best SuperCircuit, and then we can train that from scratch, and then to do the evaluation on the real machine. So another additional step we can optionally add to the whole process is the gate pruning. So the idea is very straightforward. So if we find some gates in the like ansatz which have rotation angles very close to 0, we can just set that 1 to 0, and then equally like basically just remove that gate, right? So we can set some of the gates, small gates, to the 0, and then remove that, and then we can do several steps of the fine tuning of the remaining parameters to recover the accuracy, and then we do another round of pruning. So that is a progressive gate pruning of the variational quantum circuits. So in that case, we can largely recover the accuracy, but because we have fewer number of gates, so we can reduce the impact of noise from those removed gates. Okay, so for the benchmarks, we use both the quantum machine learning task and also the variational quantum eigensolver task. So the QML, we test that on the MNIST and also Vowel dataset and also the fashion MNIST. And VQE task, we use the hydrogen, water, and also 3 other molecules. So the quantum device we were using were IBM Q machine with qubits from 5 to 65 and quantum volume from 8 to 128. So here is the quantum neural nets we are building to do the classification task. So we don't have theoretical proof of using this quantum neural nets can bring significant benefit to classical one, but because this is a sort of a very interesting variational algorithm, so we do this as part of the benchmarking. So the quantum neural nets here, we try to do the classification. So the input is an image. So we can see there's a 2 because we do some downsampling. And then we can encode the pixels as the rotation angles to using those rotation gates to the quantum phase. And then we have the trainable quantum layers, which are actually the onside we try to search. And finally, we can do the measurement on, say, the D basis or other ones. So in this example, we measure in the D basis, and then we do some post-processing of the measurement result to obtain the machine learning task final classification result. So say we can use softmax to obtain the probability of each class. So and also for the VQE, we have the variational onside state preparation circuits in the first place, and then we have the polystrings to do the measurement and then do a weighted sum to obtain the final ground state energy estimation of the molecule. Okay, so here we show the result of the quantum neural nets on the MNIST 4. We have 2 baselines. One in yellow is the noise unaware search, which means we use the SuperCircuit, but during the search process, we don't evaluate with the noise on the real machine. We just evaluate on noise-free setting. So in that case, the model will typically the larger the better because of the no noise impact. And also we have the human design, which we refer to some of the previous quantum neural nets in Seth Loy's paper and also several other professors' paper. So we compare to the human design in their paper to with their basic box. So we can see that the performance here, the QuantumNAS can have better accuracy compared with the peak of the other method. And also we can delay the accuracy peak, which means the trade-off is can be improved. So the accuracy on the 4 classification result is around 90%, and for the 2 classification we have around 95% on the IBM Q Yorktown machine. Yes. So right. So the number of parameters here. So if we say testing the noise-free accuracy, those are typically saturated at a pretty high level, say 95%. But the real measurement accuracy is degraded because of the noise.
Here, when you say noise, what do you mean exactly?
So that's the all the errors, the gate errors.
Coherent, incoherent, all that.
Yes. So because we just measure the results on real machines, so we basically consider all the noise.
Okay. And I guess the follow-up question would be: have you might be talking about this in a couple of slides, but have you compared the parameters that you have between your quantum, I guess NAS versus the noise unaware search?
You mean compare the values or the?
Yeah. So you have. And this is QML, how many arbitrary rotation parameters you have. So
Oh, I see.
How are those rotation parameters different?
You mean the values of the parameters or the number, the total number of the gates?
No, just the value of the parameters.
Okay, that's interesting. So we actually compare the number of gates, but didn't see what's the exact value of the rotation angles. So
Is it?
You're also updating structure, right?
The what?
Are you also changing gate configuration?
Yes. We changed the structure is different. Yeah. Right. Mm-hmm. Yeah, the QuantumNAS one is the search one, and for other ones are just the design.
And the reason I was asking this question is that, so I mean, based on what I've seen or we've seen before, the dominant source of noise, especially when it comes to performance of QML or VQE with these various algorithms, is the
Over rotation?
well, not over rotation actually. It's typically the residual ZC that's on
Okay.
when you do two different gates.
Oh, yeah.
What I was curious about to get to is that if that's something that we can get out of, just or by looking at or comparing your quantum smart design versus the non-quantum research.
I see. Right. So yeah, I think that's a very interesting point.
We can talk about it.
Yeah, sure. Yeah. Sure. Yeah. Okay. So we also compare the result of the result on the hydrogen on different device. So we use different design spaces, which means the initial SuperCircuit construction space is different. So we also we compare to say random generated ansat and also human design ansat or noise on wire search or the UCCSD ansat. So we can see that the result of the QuantumNAS on the real machine is closer to the optimal solution. Also, we are also trying to do some more complicated task, which is the 10 class classification. So which is the MNIST 10 class. So the result is basically for all the other method, we can see around 10% to 15% of accuracy. So just marginally higher than the random guess. So with the QuantumNAS on the Melbourne machine, we can achieve around 32% of the accuracy. So right. And also we want to emphasize that the scalability of the method is can scale to the large machine because we can do all the training and the search and also the final SuperCircuit training all done on the real machine because we can use the parameter shift or other non-differentiable method to obtain the gradients. Yeah. So, okay, so another one is the effectiveness of the gate pruning. So here we can see in the yellow column we have the QuantumNAS result, and the right column is the QuantumNAS plus pruning. So we can see some of them can obtain around 3% of the improvements. That is because in the noise-free setting we have very similar accuracy, but after prune some of the gates, we can reduce the impact of the noise, so we can see some small benefits from the pruning. And also here we show the training speed. So that is training using our library on the GPU. So we can see that on using the 4 qubits, the SuperCircuit training is around just 30 minutes. And for 21 qubits, the SuperCircuit training on one GPU card is 20 hours. So we can do the scale up to around 30 qubits with multi-GPU training. So that is much faster than the Qiskit training steps, which typically the first row will take several hours, and for 15 qubits that will take several days in the Qiskit. And also because of we just do the training for once and search for the SuperCircuit, we can also reduce the search cost from a very large number of GPU hours to a pretty small one. Because in the first large one, we need to train each of the candidates in the design space. Okay, so next several minutes, I will just give a brief introduction of our TorchQuantum library, which is open source library for differentiable quantum simulation. So there are several features. The first one is that we construct all the basis operations and also the basic data structure using the PyTorch native ones. So for example, if we are doing the state vector simulation or density matrix simulation, we can use the PyTorch tensor to construct those state vectors and also the matrices. The second point is the dynamic commutation graph. So that means after we apply a gate, so if we use Qiskit, we need to first append many of the gates to a circuit, right? In that case, we are constructing a static graph. So that static graph is transpiled and then sent to the backend to run. In that case, if we want to know what is the state after I just apply, say, a Hadamard gate to the current state, what is the result? It is pretty difficult to obtain that. because the graph is static. But in the TorchQuantum, it is very convenient because after we write one line of code of adding one gate, the operation is already done. So we can see the immediate result of the state vector or the density matrix because of the dynamic computation graph. That is pretty easy for beneficial to the debugging process. And also the third point is the gradient support. So if we want to do variational circuits, many of times we want to obtain the gradients. So we use the PyTorch native auto-grade support, so we can, after specifying the loss function, we can obtain all the gradients in the middle. And also during the training, we can leverage all the optimizers, those fancy like item optimizers. Those are very off the shelf in the PyTorch framework. And also another feature is the batch mode inference and training. So in the Qiskit, if we want to run many circuits, there is a for loop. So we need to for 1 to n circuits and run them one by one, right? But in the TorchQuantum, we can inference or simulate all the circuits together because the tensorization of the state vector. So say if we have many different initial states from the quantum sensor, and then we can simulate, say, 100 quantum states using the same ansatz and get 100 result quantum state. So we can run that just with a tensorized operation on GPU. So that is very fast. Sorry. Okay, so another point is the easy deployment on the real machine. So we have a push button solution to convert the PyTorch circuit to the Qiskit quantum circuit. And then we just need to add one line of code, and then all the circuit will be converted to the Qiskit, and then we can specify the backend to run on the real machine or using the Qiskit simulators. And also because of the PyTorch support, we can seamlessly to pass the tensor from the quantum state to the classical neural nets. Say we want to use some convolution neural nets to do post-processing, or we want to use some other transformers. Those fancy stuffs, we can very easily plug them into the quantum circuit results to do the post-processing. And the whole process is differentiable. And also, we are currently under development is the pulse level simulation. So we also want to make sure we want to implement the differentiable master equation solutions and also the Schrodinger equation solutions solving process.
Do you plan to make like a connection with CERC or other? Yes.
So we have planned to connect to CERC and also the several libraries in Julia, like the YAO library. So we want to have some conversions to them. Yeah. The current mature one is to the Qiskit. Yeah, because of their available machines. Yeah. Right. And also we will have a tutorial on the quantum computing engineering quantum week this year. Okay, so let's just very briefly have a look at the underlying implementation. So we have the state vector here, so we can use the PyTorch states to initialize that. And then for say for a CNOT gate, we can use this matrix to put that to the PyTorch sensor, and then we can do the matrix vector modification in the PyTorch. And also for parameterized quantum gates, we can specify the parameters, and then we just put the parameters, do some computation here, and then construct the matrix, and then we can return the resultant matrix with the specified rotation angle, and then we apply that to the state vector or density matrix. Use the torch ion sum or torch BMM operations. Here we can also have a brief look of the MNIST example with the TorchQuantum. So the construction process is very similar to the PyTorch. So in the PyTorch, typically we have in each of the module, we have an init function which specify what is in the model, and then we have a forward function called forward to specify how can we use those models. So the init is the construction process, and the forward is the usage process. So here we can say initialize a quantum device, and then we can specify the number of qubits here. And then we can also specify the poly-Z operation on all the qubits. And then we can specify some of the encoder gates to encode the image to the quantum states. And then we can have some trainable gates as the TQ TorchQuantum .rx gate. And then we specify it has parameters and also trainable. And then during the forward pass, the input is the image, and then we can do the downsampling of the image to 4x4, and then we reset the state, which is similar to reset the quantum state on real machine to all 0 state, and then we encode the classical values to the quantum machine using the gates, and also apply the trainable gates, which is just like this line. We use self rotation x gate 0, and then we apply that to the quantum device and specify which qubits we want to use. And then we can also apply some non-trainable gates on the fly. So say we want to use the hammer gates on the fourth qubits, or we want to use SX to the third qubits. So during the forward process, after we write this line of code, we can print the states of the quantum device and obtain the result immediately. So that process is dynamic. So we can debug what is the wrong states in the middle. Yeah. And finally, we can do the measurement from the quantum device. So this process get the expectation value on the poly-Z basis, and then we can do some post-processing on the classical side. So we can say do any say we want to apply 40 connector layers. That is very simple to just apply to X, or we just want to do softmax or the summation or other operations. We can just apply to the X. And also here we have QuSCIT processor, so which help us to process the whole model on the real machine. So here we just need to initialize a QuSCIT processor, which specify use real quantum machine as true. And also the backend name is the Yorktown machine, which is also called MMQX2, which is retired now, unfortunately. And also in the repo we changed to Quito, so hopefully lasts longer. And then we can set the QuSCIT processor to the model we just constructed. And then during the real running forward pass, we can already like run that on the real machine. Okay, so those are also some of the videos we recorded. We have a collab on the Google GPU on the Google Colab. So if we use that, we can use free GPUs. So and then we don't need to set up those servers, so we can leverage GPU power. We have several collabs and also the videos like explaining those collabs step by step. So which is help the users to get familiar with the library. Okay, so
welcome to our collab. Hello.
Okay, so as conclusion, we have the TorchQuantum library, which is a fast differentiable open source library for quantum simulation, and also we introduced the QuantumNAS. So all the QuantumNAS algorithms are implemented in the TorchQuantum. So we also have the examples of TorchQuantum. And also many of other examples like the quantum kernel methods or quantum convolution method. So welcome to check out, and welcome to give any feedback. So we are trying to find super users, and you can contact me, and then I will do the debugging for you in 1 minute. So right, so we are eagerly find users of our library. Yeah. So thank you for listening, and I'm happy to take any questions. If no question for me, I have one question for you. So do you typically use a Q-tip or QuSCIT to do the simulations?